Hello students, welcome to EPG Pathshala. I am Dr. P.K. Ahluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about a module, Ensemble Theory, Classical, Part 3, Microcanonical Ensemble, under the paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We will see the importance of Planck's constant in enumerating the number of allowed microstates in the light of Heisenberg uncertainty principle, recognize the constraints under which microcanonical ensemble is defined and characterized by thermodynamic variables, write the microcanonical density distribution function, clarify why a small amount of arbitrarily small uncertainty in energy delta E around E is needed to count total number of allowed microscopic states. This module has been developed for postgraduate level as per the following subtopics: phase space and number of microscopic states, microcanonical ensemble distribution function, with following applications: a two-level system, classical ideal gas, a system of linear classical harmonic oscillators, a system of spin half particles. Calculate allowed number of microstates and hence entropy in an arbitrarily thin shell of a given microscopic ensemble for sample prototype models such as classical ideal gas, a two-level system, a system of classical harmonic oscillator, magnetization of a system of spin half particles. In this module, we will study the highly constrained ensemble, the so-called microcanonical ensemble, representing a system having constant energy E, constant number of particles N, and constant volume V. It describes a system which is completely isolated system from its surroundings, a highly idealized situation seldom encountered in real situations. Within these constraints, particles of the system can be in any one of the allowed microstates with equal a priori probability. Following the prescription described in last module, an effort is made to count the allowed total number of microstates which help us define the probability of each state, followed by calculation of entropy, which can then be used to calculate the thermodynamic properties of the system under study. But before embarking on this plan for microcanonical ensemble, we shall underline the importance of Planck's constant in the light of Heisenberg uncertainty principle in counting the microstates in the allowed phase space of the system under study. Phase space and number of microscopic states. As yet, till this point, we have described the enumeration of microstates in terms of calculating the volume of the allowed phase space. This enumeration of microstates is possible through Heisenberg's uncertainty principle, according to which phase space can be regarded as made up of elementary cells of the minimum volume h raised to power d, where d is the dimension of the phase space representing single particle quantum state. In the case of an n-particle system with phase space having 6 n dimensions, d is equal to 3n. Microcanonical ensemble distribution function. To define the microcanonical distribution function, we must ponder on a crucial question: can we have an absolutely isolated system? Because in actual systems, there is always some contact with the surroundings, and system doesn't have a sharp value, and it will have a width delta around E. Hence, system has a range of energy values lying in the interval E minus half delta and E plus half delta, where delta is small compared to U. Values lying between the interval E minus half delta and E plus half delta, where delta is small compared to E. Doing this implies that a system has a large number of possible microstates in the phase space lying anywhere between a hypershell are equally a priori probable, such that E minus half delta is less than equal to H is less than equal to E plus half delta, where Capital H here is the Hamiltonian. This defines a region is in phase space having volume omega is equal to integral of theta function of E plus half delta minus H multiplied by theta function of H minus E plus half delta over the phase space where theta represents a unit step function defined by theta x is equal to 1 if x is greater than or equal to 0 otherwise. The step function sitting as integrand restrict the region of integration defined by equation 1. It is obvious that allowed phase space volume is a function of energy E, number of particles n, volume V and delta. Then a microcanonical ensemble is a collection of systems for which probability distribution function rho qp in equilibrium is given by rho qp is equal to constant for E minus half delta less than or equal to H less than or equal to E plus half delta and equal to 0 otherwise. Now, if f as a function of qp is a physical quantity, then the microcanonical ensemble average is given by integral of rho qp multiplied by f qp over the whole phase space divided by integral of rho qp over the whole phase space, which is in fact then equal to, because rho in the numerator and the denominator come out are constant and cancel, making it equal to integral of fpq over whole phase space divided by integral of the phase space. Now we will look at the applications of microcanonical ensemble. As a first example, we will take a two-level system. Let us begin with a simple two-level system, that is, a system which has only two states accessible, consisting of n non-interacting particles. Figure 1 shows such a situation. The lower level is the ground state of the system with zero energy, and the other level is the first excited state of the system with energy epsilon. Both the states are non-degenerate. The higher energy states are not available to the system because they exceed the total energy available to the system. Let n0 and n1 be the number of particles in the ground state and first excited state respectively, such that n is equal to n0 plus n1. The energy of the system is E is equal to n1 times epsilon. If we assume particles to be distinguishable, then the number of microstates is the number of possible ways of choosing n1 particles out of total n particles to fill the excited level, which we call omega, and is given by omega is equal to a combination of n and n1, which is equal to n factorial divided by n minus n1 factorial and n1 factorial. Since we are dealing with a thermodynamic system with large n and n1, we can apply Stirling's approximation to calculate entropy S of the system at equilibrium using Boltzmann relation S is equal to Kb log of omega. We get S is equal to Boltzmann constant multiplied by n log of n minus n1 log of n minus n1 minus n1 log of n1. Noting that n1 is equal to E upon epsilon, this equation 7 becomes S is equal to Boltzmann constant multiplied by n log of n minus E upon epsilon log n minus E upon epsilon minus E upon epsilon log of E upon epsilon, which can be simplified further as S is equal to Kb, the Boltzmann constant, multiplied by E upon epsilon minus n log of 1 minus E upon n epsilon minus E upon epsilon log of E upon n epsilon. Here log is to the base E. Equation 9 provides us entropy for the system as a function of extensive variables E and n. Now we are ready to get all other measurable thermodynamical quantities like temperature T, energy E, and specific heat Cv. Recalling that temperature can be obtained by using the relation 1 upon T is equal to partial derivative of S with respect to E at constant N and constant V. 1 upon T is equal to Boltzmann constant divided by epsilon whole multiplied by log of 1 minus E upon N epsilon plus E minus N epsilon multiplied by N epsilon divided by N epsilon minus E multiplied by minus 1 upon N epsilon minus log of E upon N epsilon minus E into N epsilon upon E multiplied by 1 upon N epsilon bracket closed, or 1 upon T is equal to Kb upon epsilon multiplied by log of 1 minus E upon epsilon minus log of E upon N epsilon, or 1 upon T is equal to Kb upon epsilon multiplied by log of N epsilon over E minus 1. Equation 12 also then gives expression for energy E as E is equal to capital N epsilon divided by 1 plus E raised to power epsilon by kBt. This effectively means N1 is equal to total number of particles divided by 1 plus E raised to power epsilon by kBt. The molar specific heat capacity when capital N is equal to Avogadro's number can be obtained by recalling Cv is equal to delta E by delta T at constant N and constant V, which gives Cv is equal to Kb multiplied by Avogadro's number N multiplied by epsilon upon kBt whole square multiplied by e raised to power epsilon upon kBt divided by e raised to power epsilon upon kBt plus 1 whole square. Let us look at some limiting cases. Case 1, when epsilon upon kBt is greater than or equal to 1, that is T approaches 0. According to equation 14, then denominator e raised to power epsilon by kBt plus 1 is very large and N1 approaches 0. This means that all particles are sitting in the ground state. Total energy E is equal to 0 and omega is equal to 1, and hence entropy S is equal to 0. Case 2, epsilon upon kBt is very much less than 1, that is T is approaching infinity. According to equation 14, under this limit, since e raised to power epsilon upon kBt approaches 1, denominator becomes equal to 2 and hence N1 is equal to N upon 2. That is, half the particles are in first excited state and half in the ground state energy of the two level system. Is E is equal to N epsilon by 2 and hence entropy S is equal to Kb N log of 2. Let us look at the behavior of molar specific heat Cv in both the limiting cases, that is case 1 and case 2. According to equation 15, C1 approaches 0 and has maxima at T is equal to 0.42 epsilon divided by Kb, or epsilon upon Kbt is equal to 2.38. This is obvious in figure 2 adjoining. This is obvious in figure 2. The Schottky anomaly found here is a characteristic feature of the system having a pair of low-lying energy levels with other levels of the system lying at a much higher level. Now we will look at the second application, which is our prototype example called classical ideal gas. In module 8, we discussed at length classical ideal gas from statistical mechanics route. Here we shall revisit this from the point of view of the definition of microcanonical distribution function defined in equation 4. Accordingly, the volume of the phase space accessible to the phase points in the microcanonical ensemble is omega, where omega is equal to an integral over whole of the phase space primed. Here, prime on the integral sign indicates that the particles are fixed in a volume V and the total energy of the system, which in this case of ideal gases kinetic energy lies between the limits E minus half delta less than equal to pi square upon 2m less than equal to E plus half delta. Furthermore, since Hamiltonian is a function of pi only, the integration over the position coordinates can be performed yielding a factor of v raised to power n. The remaining integral is the volume of a 3n dimensional shell enclosed by two hyperspheres of radii square root of 2m multiplied by E minus half delta and square root of 2m multiplied by E plus half delta. For delta very much less than E, it is thickness of the shell, which is delta multiplied by m upon 2e raised to power half times surface area of the 3n dimensional hypersphere of radius square root of 2me. In module 10, we had derived it for an n-dimensional hypersphere and is Sn is equal to 2 pi raised to power n by 2 divided by n by 2 minus 1 factorial whole multiplied by r raised to power n minus 1. Thus, volume of the desired 3n dimensional hypershell is delta multiplied by m upon 2e raised to power half multiplied by 2 pi raised to power 3n by 2 divided by 3n by 2 minus 1 factorial multiplied by 2me raised to power 3n minus 1 divided by 2. Therefore, the phase space volume accessible to the representative points of system on rearranging is given by omega is equal to approximately delta by E multiplied by v raised to power n into 2 pi m e raised to power 3n by 2 divided by 3n by 2 minus 1 factorial. Hence, the number of microstates is capital omega is equal to small omega divided by h raised to power 3n, which is equal to 3n by 2 multiplied by delta by E multiplied by 2 pi m into E v raised to power 2 by 3 divided by h square raised to power 3n by 2 divided by 3n by 2 factorial. Therefore, entropy is given by S is equal to k log of omega, that is S is equal to kbn whole multiplied by log of v 2 pi m upon h square raised to power 3 by 2 minus 3 by 2 log of 3n by 2 plus 3 by 2 plus 1 upon n log of 3n by 2 multiplied by delta by E. For large n, the last term in the expression is negligible. Hence, S is equal to kbn multiplied by log of v multiplied by 2 pi m e upon h square raised to power 3 by 2 minus 3 by 2 log of 3n by 2 plus 3 by 2. This expression, though expresses entropy S as a function of energy E, volume V and number of particles n, but is still not correct and needs to be corrected for indistinguishability, which led to Gibbs paradox. Once the expression is corrected by dividing omega by n factorial, the other thermodynamic properties can be calculated as was found in earlier module. Now we will look at another interesting problem of physics, a collection of linear harmonic oscillators. This is a problem which we encounter very often. For example, in solid state physics, to look at a solid as a collection of harmonic oscillators. Here, we are interested in a system of n harmonic oscillators of same frequency omega in microcanonical ensemble with total energy E. The Hamiltonian of the system is given by H is equal to summation over I is equal to 1 to n pi square by 2m plus half m omega square qi square. We shall look at this problem as a collection of classical oscillators and a collection of quantum mechanical oscillators and compare the two results later. First, we will look at classical approach. Classically, it amounts to finding the volume of the phase space omega within the hypershell of the radii lying in the interval E minus delta less than equal to summation over I is equal to 1 to n pi square by 2m plus half m omega square qi square less than equal to E. This is omega is equal to delta times the surface area of the volume of the phase space bounded by the surface summation over I is equal to 1 to n pi square by 2m plus half m omega square qi square is equal to E, which is the derivative of the phase space bounded by the surface summation over I is equal to 1 to n pi square upon 2me plus qi square divided by E upon half m omega square is equal to 1. The volume of this 2n dimensional hypersphere can be obtained from the volume of the generalized sphere in an n dimensional space bounded by the surface summation over I is equal to 1 to d xi square divided by ai square is equal to 1, given by Vd is equal to pi raised to power d by 2 divided by d by 2 factorial multiplied by the product of ai's I taken from 1 to d. Using equation 22, we get volume V corresponding to 2n dimensions is equal to pi raised to power n divided by n factorial multiplied by 2me raised to power n by 2 multiplied by 2e by m omega square raised to power n by 2, which on simplification gives 1 upon n factorial multiplied by 2 pi e by omega raised to power n. Therefore, the surface area can be obtained by taking derivative of 23 with respect to E, and one gets surface area of 2n dimensional space is equal to dV by dE is equal to 1 upon n factorial multiplied by n multiplied by 2 pi by omega raised to power n e raised to power n minus 1 is equal to 1 upon n factorial multiplied by 2 pi e upon omega raised to power n multiplied by n upon e. So, the volume of the hypershell of phase space with allowed representative points is given by omega is equal to 1 upon n factorial multiplied by 2 pi e upon omega raised to power n multiplied by n delta upon e. The number of microstates omega are given by small omega divided by h raised to power n, which is then given by omega is equal to 1 upon n factorial 2 pi e upon h omega raised to power n multiplied by n delta upon e. Entropy of this collection of n linear harmonic oscillators is then given by S is equal to n kb multiplied by log of 2 pi e upon h omega minus log of n plus 1 upon n log of n delta upon e. The last term in 27 can be neglected since it has a very small contribution compared to other terms. Therefore, we can write S is equal to n kb log of 2 pi e upon n h omega plus 1. Now, we are ready to calculate other thermodynamic quantities such as temperature and Helmholtz free energy. Temperature is given by 1 upon T is equal to partial derivative of entropy with respect to energy at constant volume and constant number of particles, which is equal to n kb multiplied by n h omega divided by 2 pi e multiplied by 2 pi upon n h omega is equal to n kb upon e. Also, we get from here E is equal to n kbt. Helmholtz free energy can now be obtained using the relation F is equal to E minus Ts. F is equal to therefore equal to minus T n kb multiplied by log of 2 pi e upon n h omega, which is equal to n kbt multiplied by log of h omega divided by 2 pi kb t. Now, we will look at this problem from quantum approach. Quantum mechanically, each oscillator has an energy eigenvalue given by well-known relation epsilon I is equal to ni plus half h bar omega, where ni is an integer greater than equal to 0. The total energy of the system is then given by E is equal to n plus capital N by 2 multiplied by h bar omega, where small n is equal to n1 plus n2 plus n3 and so on up to nn, which is a non-negative integer. Now, to calculate the number of microstates corresponding to this total energy, let us note that this amounts to distributing n packets of energy in n boxes, where each box can contain any number of packets, including possibility of 0 packets. If we wish to create n boxes in a box, we require n minus 1 partitions. So, to count the number of possible ways to distribute n energy packets in n boxes is equivalent to arranging a total number of n packets and n minus 1 partitions together. That is, permuting small n plus capital N minus 1, out of which small n packets among them are indistinguishable and n minus 1 partitions among them are indistinguishable. For example, the following diagram shows arranging n distinguishable particles in n boxes with n minus 1 indistinguishable partitions. Therefore, omega is equal to small n plus capital N minus 1 factorial divided by small n factorial multiplied by n minus 1 factorial. The entropy of the system after using Stirling's approximation is then given by S is equal to Kb log of omega is equal to Kb multiplied by n plus capital N minus 1 log of n plus capital N minus 1 minus small n log of n minus capital N minus 1 log of capital N minus 1. Since in thermodynamic limit n is very much greater than 1, n minus 1 is approximately equal to n and small n is equal to E upon h bar omega minus n upon 2. Equation 35 therefore becomes S is equal to Kb multiplied by E upon h bar omega plus n by 2 plus log of E by h bar omega plus n by 2 minus E by h bar omega minus n by 2 log of E by h bar omega minus n by 2 minus n log of n, or S is equal to n Kb E by nh bar omega plus half log of E by nh bar omega plus half minus E by nh bar omega minus half log of E by nh bar omega minus half. Now we are ready to derive all thermodynamical relations. Reciprocal of the temperature is given by partial derivative of entropy with respect to energy at constant n and constant volume, which is equal to Kb upon h bar omega multiplied by log of E upon nh bar omega plus half minus log of E upon h bar omega minus half, or E upon h bar omega plus half divided by E upon n h bar omega minus half is equal to E h bar omega by kBt. This implies E is equal to n times h bar omega multiplied by half plus 1 upon e raised to power h bar omega by kBt minus 1. It is interesting to ask what happens to equation 40 in a quantum mechanical result in the classical limit, that is 1, h bar omega by kBt is very much less than 1, and one finds that E is approximately equal to capital N multiplied by h bar omega by 2 plus h bar omega multiplied by kBt divided by h bar omega, which is approximately equal to n kBt, and it is the same result as we got in the case of classical case. Furthermore, specific heat at constant volume Cv is equal to partial derivative of internal energy with respect to temperature at constant n and constant V, which can be obtained as Cv is equal to n kb multiplied by h bar omega by kBt whole square multiplied by e raised to power h bar omega by kBt divided by e raised to power h bar omega by kBt minus 1 whole square. In the classical limit, it becomes Cv is equal to n kb h bar omega by kBt whole square multiplied by 1 upon h bar omega by kBt whole square, which is equal to n kb. Once again, the classical result. Similarly, Helmholtz free energy in quantum and classical limits can be obtained. Figure 3 shows the graph of E upon n h omega versus kBt upon h omega for quantum mechanical and classical harmonic oscillators. It is worth noting that when kBt upon h bar omega becomes large, the quantum mechanical results approach classical results. Figure 4 here represents a graph between specific heat at constant volume divided by n kb versus kbt divided by h omega for a collection of n harmonic oscillators. Once again, one sees that the quantum mechanical results approach classical results when kbt upon h omega becomes large. This example actually represents model of an Einsteinian solid made of n uncoupled quantum oscillators of same frequency. Now we go to another system, a system of spin half particles. That is, we now consider an isolated system of n particles of spin half, that is, sigma I is equal to half h bar omega multiplied by unit vector in the direction of z axis, which is equal to sigma zi multiplied by the unit vector in the direction of z axis. Each particle in the system therefore has a magnetic moment mu sigma placed in a magnetic field H. Such a particle has only two orientations, spin up or spin down with respect to the magnetic field. Let the magnetic field be in the direction of z axis. Then the Hamiltonian for such a system is given by H is equal to minus summation over I is equal to 1 to n mu sigma I dot h, which is equal to minus mu h summation over I is equal to 1 to n sigma I z. Note, the Hamiltonian does not have a term for the motion of the particles except interaction with the magnetic field. System has a number of particles and the total magnetic moment capital M as extensive parameters. Volume has no role to play in this situation. Suppose that at equilibrium, system has n plus particles with spin up and n minus particles with spin down, such that capital N is equal to n plus n minus. The net magnetic moment of the system is then capital M is equal to mu times n plus minus n minus. Solving 45 and 46 for n plus and n minus, we have n plus minus is equal to n by 2 multiplied by 1 plus minus capital N upon mu capital N. So, to count the number of microstates, it is merely a matter of selecting n plus number of particles out of capital N particles and is given by omega mn is equal to n factorial divided by n plus factorial multiplied by n minus 1 factorial. Entropy can then be obtained from Boltzmann relationship S is equal to kb log of omega mn as Smn is equal to kb log of n factorial minus log of n plus factorial minus log of n minus factorial. In thermodynamic limit using Stirner's formula N47, we have Smn is equal to kb multiplied by n log of n minus n by 2 multiplied by 1 plus capital M divided by mu n multiplied by log of n by 2 1 plus m upon mu n minus n by 2 multiplied by 1 minus m upon mu n multiplied by log of n by 2 multiplied by 1 minus capital M by mu n, or Smn is equal to n kb multiplied by log of 2 minus half 1 plus m upon mu n log of 1 plus m upon mu n minus half multiplied by 1 minus m upon mu n log of 1 minus m upon mu n. Equation 51 is the entropy of the system in terms of extensive variables capital M and capital N. Knowing that partial derivative of entropy with respect to capital M at constant t, constant v and constant n is equal to minus h upon d, we have minus h upon t is equal to kb upon 2 mu log of mu n minus m divided by mu n plus m, which can be further simplified to give the expression for magnetic moment, that is capital M is equal to mu n multiplied by e raised to power mu h by kbt minus e raised to power minus mu h by kbt divided by e raised to power mu h by kbt plus e raised to power minus mu h by kbt, which is equal to mu n times tan hyperbolic mu h by kBt. This is the equation of state of a system with n particles of spin half. Before we end, it will be interesting to explore log of omega as a function of m and n. Noting that for 0 less than x less than 1, log of 1 plus minus x is approximately equal to plus minus x square by 2 plus minus x square by 3 minus so on. We have log of omega mn is equal to n log of 2 minus half capital M upon mu n whole square, or we have omega mn is equal to e raised to power log of 2 multiplied by e raised to power minus 1 upon 2n multiplied by m upon mu whole square, which is approximately equal to e raised to power minus 1 upon 2n m upon mu whole square. This is a Gaussian distribution with a spread of square root of n as shown in figure 5. So students, let us summarize what we have learnt in this module. In this module, we have learnt that microcanonical ensemble corresponds to a collection of exact replicas of completely isolated system with E is equal to constant, N is equal to constant, and V is equal to constant. That microcanonical distribution function is defined as rho as a function of QP is equal to constant for H lying between E minus half delta and E plus half delta and 0 otherwise, where E minus half delta less than equal to H less than equal to E plus half delta is a thin shell of energy with width delta very much less than the total energy of the system. The microcanonical ensemble average is given by of a physical quantity F equal to integral of distribution function multiplied by the physical quantity integrated over the whole phase space divided by integral of the distribution function over the whole phase space, and that turns out to be merely equal to integral of the physical quantity over the whole phase space divided by the volume of the whole phase space. That microcanonical ensemble can be applied to study some interesting prototype problems, and following problems were studied to calculate the entropy and other thermodynamic properties. A two-level system, classical ideal gas, a system of linear classical harmonic oscillators, and a system of spin half particles. That a two-level system shows Schottky anomaly in its specific heat. Also, two-level system shows following limiting behaviors. Case 1, when epsilon upon kBt is very much greater than 1, that is T approaches 0, all the particles sit in the ground state, total energy E is equal to 0 and omega is equal to 1, and hence S is equal to 0. In the case 2, epsilon by kBt is very much less than 1, that is T is approaching infinity, half the particles are in first excited state and half in ground state. Energy of the two-level system is E is equal to n epsilon by 2, and hence entropy S is equal to kB multiplied by n log of 2. That classical ideal gas can be studied using microcanonical ensemble. The calculated entropy shows Gibbs paradox, which needs correction for indistinguishability of particles. That collection of n harmonic oscillators, also known as Einstein solid, can be looked at classically as well as quantum mechanically with following results for entropy and various other thermodynamic quantities. The left column of this table shows thermodynamic properties of a collection of n linear classical harmonic oscillators, and the right column shows thermodynamic properties of the collection of n linear quantum harmonic oscillator. Quantum mechanical results approach classical results in the so-called classical limit, that is h bar omega by kBt is very much less than 1. That a system of n particles with spin half has a new extensive variable with following equation of state. M is equal to mu times the number of particles with spin half tan hyperbolic mu h by kBt, where h is magnetic field. That a system of n particles with spin half has a Gaussian density distribution with a spread square root of n given by omega approximately equal to e raised to power minus 1 upon 2n multiplied by m upon mu raised to power 2. Thank you.